Okay. Continuous growth and decay. And I really want you to focus on this word continuous. We're going to talk about this a lot today, but you may even want to underline that on your slide. Continuous is the key word here. All right. When we did that activity, what you were seeing is what would happen if you compounded more and more often. Okay, so when you compounded annually, you got $2. When you compounded semi-annually, you got, what was it, $2.25, something like that. And the number kept kind of going up, right? But it didn't go up like exponentially. It didn't go up infinitely. It got closer and closer to a single number. Now, if you were compounding your interest at the bank every single second, that's about as close to being continuous as possible, right? That's about as often as you could possibly do it. If you were to speed it up even more, if you were to compound every half a second or every quarter of a second, what you would find is that the number gets closer and closer to that magic number you got at the bottom of your page, like 2.718, but it was a giant, giant decimal, right? Okay. So here's the things I want you to take away today, and I don't think there's anything for you to write down, but we're just going to do these. First of all, continuous growth is when exponential growth is happening constantly. It's not like every year or every month or anything like that. It's all the time, okay? And so when you compound more and more often, your answer comes closer and closer and closer to this irrational number. What does irrational mean again? Okay, what does it mean to be not rational? Okay, it's a decimal that... Nope. Good guess. Someone give me another example of an irrational number. Nope. -3 is very rational. Nope, that's still okay. There's a very famous irrational number.
0.
Okay, close. What is that number called? Pi, yeah. Pi is an irrational number. What is special about pi? Emily, put that away.
The decimal doesn't stop.
The decimal doesn't stop, right. That's what it means to be irrational. Okay? So this number that you got closer and closer and closer to, that 2.718, that's going to be a decimal like pi. The decimal is going to go on and on forever. And that's why I wanted you to write out all those decimal places. Okay? This type of growth and decay, because you can go in both directions here, this type of growth and decay is used for many growth models found in nature. So if you measure the growth of a plant over time, or population growth of insects or something along those lines, it's close. Instead of being that exponential model that we're used to, the AB to the X, it usually involves this continuous growth with this irrational number. Okay? And I'll be honest about this. Continuous interest, I've seen a lot of math problems that have to do with interest being compounded continuously, and you're going to see problems that have to do with interest being compounded continuously. Never have I walked into a bank and had them offer me continuous interest, which would be interest that was just compounding constantly. But I guess it's possible. Okay? What's that? It is echoing because I'm recording it. So, okay? Was that bothering you?
No, I kept hearing that. I thought it was like tripping or something.
Oh,
We all thought
no.
it was tripping.
Right. Okay, so calculating continuous interest. And again, your key word here is continuous. All right? If interest is being compounded continuously, then we're going to use this formula. A equals P times E to the power of RT. Okay, go ahead and write that formula in for yourself. Okay. I think you just have to write in the formula. Which I guess now would be a good time to talk about that irrational number that we were just looking at. What does the P stand for when you're talking about interest? Principal, which is the what? What does it mean to be the principal? Okay. Financially, what does it mean to be the principal? Not quite.
The initial number.
The initial number. It's the amount that you're investing. Yeah. Okay, so this is the amount you're investing here. This E value, That's that number that you were finding in that activity. Okay, E is sort of like pi. All right, it's a constant number, like it's the same number every single time you write E, and it's approximately equal to 2.718, but it goes on and on and on forever. Now the good news is you do not have to memorize that because your calculator has an E button. Okay? Yeah. Yep, and I'll help you find it in just a minute when we do an example, but you are going to be able to do E with your calculator. Yep, that's what you're going to want. Okay, what is R equal to then? If you think back to when we did compound interest. What was the R equal to? The rate, the interest rate, yeah. So this is the, I guess you can think of it as the interest rate.
What else would you watch?
All right, pull back together.
What else would you watch when they draw blood? Or watch them draw blood except when they start drawing.
R in this case, because we're talking about compound interest, that's an interest rate. Now you're going to be using that R in other formulas. Basically, that's your growth rate. That's whatever you're growing by. Now the good news for you is, remember in the other formulas when I gave you a percentage, when I said like you're going to grow by 25%, you had to do the whole add it to 100 or subtract it from 100 either way. With this formula, you do not have to. Okay, you do not have to add or subtract from 100. You can just put it directly into the problem. And then what do you think T is? Time. Good. Okay. Now here's the thing. Technically this formula, because it's got this P for principal, this formula is really only used for interest problems, where I'm giving you like a bank account, something like that. However, because that is easy to remember, A equals PERT, a lot of people end up kind of relying on that formula for everything else that we do with continuous interest too, or continuous growth, I should say. Okay, so I'm about to show you another formula. I want you to know that it's really the exact same thing as this formula, just it uses some different letters. But if this one's easier for you to remember and you just want to treat P as your initial value every time, that's fine too. So continuous growth is modeled with this equation. So N of T is equal to N sub 0 E to the power of RT. Okay, go ahead, write that down, and then we'll unconfuse you on that formula. I know we've been kind of segmented this morning. Apologize for that. So here's the thing. First of all, do you remember talking yesterday about this N sub 0 business? We did it in one of the problems we went over. Okay, do you remember what that N sub 0 really represents? Anytime you've got that little 0 there, that's a clue that you're looking at what? Okay, along those lines. And what is principal again? Okay, it's the initial amount, right? This N sub 0 is just a fancy way of saying the initial amount. What were we using for the initial amount before? What letter? Like before today. When we were doing AB to the X, it was A, right? I could take this formula, this N sub 0 ERT, and I could write it as A times E to the power of RT. Okay? Because that A is just the initial amount. This is what I'm saying, is that isn't that really the same as the P, right? It's the initial amount that you're putting in. So a lot of people always kind of rely on this formula just because PERT is kind of easy to remember, and you can just think of P as your initial value. Because otherwise, isn't this the same as this? The only difference is this one has a P and this one has an N sub 0. So I don't care what letter you use to stand for your initial value. For all of these problems, all you're doing is the initial value times E to the power of RT. Okay, that's going to get less confusing when we do some problems with it. So here's an example. If $850 is invested at a rate of 6% compounding continuously, how much will be in the account after 10 years? All right, the very first thing I would like you to do is underline this word continuously. Okay, continuously. anytime you see that word, and that word specifically, okay, it's got to be the word continuously. It can't be something that means almost the same thing. It's not going to say constantly. It's not going to say all the time. It's going to literally say the word continuously. Anytime you see continuously, I want you to be thinking of E, that you've got to use the formula that has E in it. And remember, E is that magic number that you came up with in the activity, 2.718-ish. Okay, but again, I'm going to show you how to do this in your calculator. Well, they're really the same formula. That was my point on the last slide, is that really they're just using different letters for that initial amount. Okay, so it's two different ways to write the same formula, just with different letters. So I don't care which one you use. Okay, so if I'm using that formula, all right, what's my P value going to be from this problem? 850. I'm investing 850. This E is just the number E. It's 2.718, yada, 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 but we're going to do that in our later. What's our rate? Okay, it's 6%. All I have to do with this one is make it a decimal. You don't have to add it to 100. So what is 6% as a decimal? 0.06, yep, to the power of 0.06. And then my time is... And then if I have two things in the exponent, what do I need to make sure I do with them? Parentheses. Sorry, I thought I put parentheses here. Let's see. Here we go. Okay, now let's talk about your calculators. So in your calculators, let's type 850. Go ahead and do this with me, everybody. This works on scientific calculators and graphing ones. 850. And then I want you to look for a little button. It's probably above another button, like you'll have to use the second key, that says e to the power of x. Okay, e to the power of x. Possibly above the ln key, if you see a key over on the left-hand side that says ln. And when you hit that, it's automatically going to give you e and then an exponent. It might even open a parenthesis for you, I don't remember. And then type in 0.06 times 10, close your parenthesis, hit enter. Okay. Do you get this value? $1,548, $1,548.80. Anybody not able to do that? Okay. Shall we try one more?
No.
Yes. Okay. A machine used in industry depreciates. Okay, so we going up or down? Down. Continuously, there's that magic word again. Remember, you have to see this word before you know to use E. Okay, when you see the word continuously, that's when you know to use E instead of using what we were doing before, the A, B to the X. Continuously at a rate of 25% per year. Currently, the machine is worth $28,000. Write a model to represent the value after T years. Right now it's just T. Okay, we're just going to leave it as T. So here's where I'm using that other formula. This is just technically, because it's not a bank account, we're not talking about a principal or an interest rate or anything like that. That PERT formula doesn't technically apply. But this formula is really the same as that PERT formula. So if it's easier for you to remember PERT, just use PERT. Okay? Remember that n sub 0 is my initial value. What's my initial value? What's the current value of the machine? 28,000. Okay. Then I'm going to say e to the power of r. What's my rate? Okay, now here's the thing that's weird that you haven't done before. It would be 0.25. But if we want to depreciate, it would be negative 0.25. Good. Or you already saw that when I flipped the slide a second ago. One or the other. Okay, so with these problems, the ones where you're using E, you're not adding or subtracting from 100. You're just making it positive or negative depending on whether it's going up or down. And then for time, it's just going to stay T. So this right here is my function. Okay? So if this particular company wanted to know, how can I look at the value of this machine over time? You could give them this equation and it would model sort of the drop in the value of the machine over time. Okay, so how much is the machine worth in 3 years? What are you going to do? 3 for T, yeah. Okay. And actually, this is a little misleading the way this is written. Probably it would be better to put parentheses around both of these numbers together. Okay. If your calculator needs parentheses in the exponents. So 28,000 e to the power of negative 0.25 times 3. Should it be a number bigger or smaller than 28,000? Thank you, smaller. What'd you get?
13,026.
That's right. $13,226.26. Any questions on that? Anyone not able to get that answer? Okay. What would you do with the last question? How much was it worth 2 years ago? Well, we want to go back in time. So we would make it negative 2. Now, here's maybe what you're thinking. You're thinking positive because we already made that other thing negative, right? Okay. What's going to happen up here if you do a negative times a negative? It's going to become positive, yeah. All right? Which means my answer is going to be bigger or smaller than 28,000? Bigger, which makes sense, right? Because if it's worth 28,000 now, then 2 years ago it was probably worth more. All right, if it's depreciating. What do we get for an answer for this one?
46,164.
Whoops. Yep, that's right. 46,164. Oh. Twitter notifications. That's awesome. Did that pop up on the screen? Okay. Just wondering if it did. Questions on any of that? All right, 10 more seconds. Big takeaway today. This is your big takeaway. I don't care if you write this down or if you just pay attention, but I want to wrap this up because I feel that we were a little bit disjointed today. When you see something is growing continuously or depreciating continuously, you're going to use one of your formulas with E. Okay? And E is that magic number, 2.718, blah, blah, blah. Okay? It's irrational. In case on like a test I were to ever ask you, is it rational or irrational? This way you would know the answer, right? It is irrational. And your E formula, the basic version of the E formula is starting value times E to the power of rate times time. And if it's interest, they might use a P here instead of an A.
Why is there a pi day but not an e day?
That's a good question. Well, I guess because pi is 3/14, March 14th. This would be 2/71. That's not really a date. But you're right, E is far less celebrated than pi.
Well, pi, because you can just eat a pie on pi.
That's true. Pi day would probably be a lot more fun.
You can
Okay.
write e's on e day.
Questions about any of this? Are you ready to tackle some of these? What's the word you're going to look for?
Continuously.
Continuously, all right? And it's got to be specifically either it's going to say continuous or continuously, all right? No other version of the word. It's got to be that word specifically, okay? Let's try some homework.